resource control. Resource control is a bit of a mixed bag of a number of different topics. One is evaluation criteria for synchronous primitives, or for synchronization primitives. How can you categorize all these synchronization primitives which you have seen so far, or design new ones? What would be a good one? What kind of synchronization primitive do you want? A little bit about general double interaction problems and liveness in double interaction environments. And then we are going to resource reclaiming. Resource reclaiming is interesting because it gives you a second level, a second layer of redundancy in your system. Every resource which you actually at runtime don't utilize, because in a real-time environment what you have been doing is you have done your worst case analysis. You estimated, does it fit if everything works out the worst possible case? You say, yes, it does. But what do you do if it actually is not always the worst case? If it works out smoother and faster in real life? You just twiddle your thumbs and say, well, I know I have a free CPU now, but actually the next task is only scheduled at 3 o'clock, so let's not do anything so far. Or do you just go, well, anybody who wants it, go. You don't do that. Because that is a recipe for absolute disaster. If it would be that easy, there wouldn't be a chapter in the lecture here about it. If you just do that, you will most likely introduce new deadlocks you have never dreamt about before, and you will delay tasks which have been running on schedule beforehand. So you cannot do it that blindly. You have to do it more sophisticated than that. Okay. This is why resource reclaiming is quite a chapter. Resource reclaiming, the motivation around is, of course, if I can utilize that, I have more possibilities for fault tolerance and handling of exceptional situations. So if something goes bad, and I'm using resource reclaiming and other redundancy schemes, I'm more robust overall. With any kind of additional support system and scaffolding around it, of course, it always also is true that if the resource reclaiming is more expensive than all the rest of your system, and you make more mistakes in programming your resource reclaiming system, and you didn't gain anything in net in the end. And general resource reservation schemes. So, first a little bit generic. Synchronization schemes, service requests. How can we categorize a service request? By which service request do you accept? You have a bunch of requests from the outside world. Which of them is going to be handled first? You can handle them by type. For example, reading requests have a higher priority than writing requests. This is handling it by type. By time of arrival, if that's measurable, if that's an appropriate scheme. By any kind of priority, very common. It's also what you get by default in your Ada environment without asking for anything else. Sorting them by some form of attributes or maybe parameters of them. We'll see why this is dangerous but thinkable. Or selecting them based dynamically on the internal state of your server. So sometimes this one is preferred, sometimes that one is preferred, depending what kind of internal state your server is, or the internal state of anything else. Possibly contradicting expressive power and ease of use. How much do you want to overcomplicate your synchronization schemes? You want to have a single operation which can do message passing, 5 parameters, dispatching, entry families, and handling shared memory at the same time. with lots and lots of parameterization and attributes around it, or you want to keep it simple, or you want to keep it distributed. How do you prevent errors in the process? Can you design them so that you cannot use them wrongly? Examples are, again, if you have synchronization mechanisms which are on the bare principles of individual mutexes or semaphore. Yes, this is about as flexible as it gets, and yes, this is also about as error-prone as it gets. Is that a natural combination? Does flexibility always imply to be error-prone? Of course, the hardcore C fans would say yes. That's why we program in C. Super flexible, nothing else gives us this kind of control and power. And yes, it's error-prone like heck, but we know what we're doing. Is that true? Is that the only way to gain flexibility? By using the most error-prone construct on the planet? Probably not to that extreme. But is it true at all? What do you lose by, concretely, what do you lose by using protected objects in terms of flexibility? I hear you enumerating hundreds of things which don't work. It's a bit of a mean example because protected objects are, of course, a quite nice example for a synchronization primitive which does not prevent you from implementing anything besides being fairly high level and completely safe from many synchronization perspectives. But it's not always working so smoothly and so easily. You find also synchronization primitives which do restrict you in practice and make it safer at the same time.
In theory, can't you just use any synchronization primitive to implement a semaphore and then just use that?
Can you just use any can you use a protected object to implement a semaphore and then take it from there? Yeah. Yeah, sure. Yes, true. And the point is? Yes, flexible without being clunky. So it's not only flexible in the sense of theoretically you can do everything, but you can also do it without lots of boilerplate and being super clunky in the process. So there are two different aspects. Can you do it at all? This is usually the case that you can't do it at all. But often you have to go through lots of different hoops to implement what you want. Okay, let's do it a bit more concretely. If you have requests from the outside, you cannot currently handle them, what is the best response for a real-time system to operate here? Are you accepting everybody in and delaying those calls internally? Or are you blocking tasks on the periphery, saying, I cannot go through with that at the moment, until I can go through completely, I block you at the outside level. If you block something at the outside level, it means that the task out there has a very easy time to change its mind. I want to have access to this motor controller here, but the interface to this motor controller says this motor is busy at the moment, but wait on the complete outside. So if you want to do something else, you can still change your mind and unblock yourself, do something else. The moment you accept it in and say, well, I can already take note of your parameters for the time being, but leave it with me. I cannot actually run the motor at the moment, but you're next in the queue. Be patient. At this point, it's much, much harder for the outside task to get out of this anymore. Practically, how can we differentiate different requests from the outside? Can we syntactically differentiate by type and priority? Yeah. pretty much in all systems. By priority alone, yeah. That's, if it's not doing that, probably not a real-time system. By order of arrival, mostly, not all systems. What do you ask for if you want to find out whether your system can actually process anything in order of arrival? Is your release mechanism fair? Do you have something like a queue underneath of sorts? Because if you don't have a queue management in your runtime system to deal with that, this guarantee cannot exist. You need to have some form of queuing the requests which are coming in. Right? Not all programming languages give you that. By the timing constraints, for example, by the deadline, you're coming in with a request that, I need this motor and my deadline is in 2 milliseconds. This is something that you cannot formulate syntactically in Ada. You would need to tap dance around that. You have to formulate that manually.
Can't you just use that as a priority instead? So making high priority something you can order above priority.
Yeah, you can do it, but you cannot explicitly syntactically express it. You cannot, for example, say this is my interface to, a message passing server or to a predicted object, and one of the parameters is my time scope. So you hand over your time scope as a parameter, and please, server, look at this time scope and evaluate that correctly. You can emulate that. Nobody stops you from handing over a record which has these kind of informations, but it's in your head. It's not, the compiler has no idea about this. That's the difference. So in Ada you cannot do this so that the compiler has any idea what you're doing here. Client attributes, in other words parameters, that works pretty much nowhere. That you can actually accept calls by the parameter. For example, you want to have a motor interface which wants to run the motor at a certain speed, and you want to process first the calls which request the higher speeds or the lower speeds, or you want to request them in an order which has increasing speed, because that saves energy if you do that. Most systems are not able to do that. You need to do this multi-stage, double interaction, accepting tasks in first, blocking them later, resorting them somehow. You cannot do this on the outer periphery level for pretty much any system. And of course, by the server state is easy. Let's run a few simple examples. Handling requests by the individual type. You want to handle things by priority, but you also want to always handle update before modify. On the outcome side, done. Easy. You just say this is an alternative statement where I can receive messages from the outside on these two channels, and please handle them in order of me writing it down in that order. Done. Can you do this on the Ada side? The priority dispatching in terms of task priorities goes without saying, similar to the Ada side. But if you want to prioritize one call over the other, then you actually need to program that manually. You have been doing that in the past. It's often usually done via the count attribute. But you just check, is there anybody waiting on the other queue at the moment? If not, I'm doing my thing. Otherwise, I'm just keeping my fingers out for the moment. Yep. There we go. And you see that the modify call is dependent on the update count is 0. Easy peasy. Let's make it a little bit more complicated. Assuming you want to run a policy of queuing up tasks and releasing them in your control. Now we are halfway towards the scheduler here. What you're doing here is you have a block and a release operation, where the block operation, I'm now not relying on the priority dispatching as built in Ada. I'm taking manual control over everything, which means I'm splitting up all of my queues into as many block queues, as many priorities as I have. This is an entry family call here, and depending on your system, on most systems you have something like 64, 100 something different priorities, which means that you have actually block replicated by this number of priorities at the moment virtually. Then I can run different dispatching policies. If you release one, if you release tasks, do you want to release only one? Do you want to release all of them, all of a specific kind? Do you want to release tasks on one specific priority, only on this priority? Do you want to release tasks on this or any higher priority? Number of different cases enumerated. How will these blocking operations look in practice? How do you implement that? The rest is just administrative clutter, which is not of any deeper importance. This is a general pattern, how you can program a blocking operation which will release your tasks based on your policy, which you're just whipping up here. Which means you have a guard, which could, for example, looking like that. Your guard is currently open if my overall state is open at the moment. And then depending on what is my release kind, if it's this priority only, then I'm releasing only if the current queue, which I'm looking at, is exactly the priority which I have set as my current priority in my overall scheduling scheme. Otherwise, I'm taking a task out of this entry if the priority of this entry is larger or equal to the current priority which I want to schedule, and all the higher queues are empty. So I'm still dispatching by priority, but I'm opening all queues from a certain priority level up. And I want to dispatch them in order of priority. And so I only dispatch if all the queues above me are empty at the moment. I factored out the function higher queues are empty. I think because I use it twice. Also because it's getting a little bit unwieldy if you write this all into the same predicates. But the predicate higher queues are empty. How do you express this in Ada? Simply for all queues which are one above to the highest queue, all the counts on those blocks have to be 0 at the moment. Nice and short, huh? I like these quantifier attributes in Ada. I'm using them wherever I can possibly do that, because doing this in one line is just nice. And inside of these blocking operations, you have then to make a decision: do I need to change the state of my dispatcher operation overall? And the state of my dispatcher operation at the moment, the important one is only, is it staying open, yes or no? And I can have a single assignment here for the Boolean state of open for my overall server state. My server state will stay open. If, in case I only wanted to release one, it will not stay open, because I just released one, so it will automatically close. So open will go to false directly. If I want to release everybody out of this specific group, then depends on, again, only this priority or this on the higher priorities. If it's only this priority, then I will keep it open if I'm still having more tasks waiting on this queue. Otherwise, I keep it open if I have more tasks waiting on this queue or any of the higher queues. And all of your scheduling schemes look basically like this. Ultimately, you just have two predicates which define the whole behavior of your dispatching and scheduling operation, which we have here. That's quite compact and nice to write. Of course, you enjoy the behind-the-scenes luxury that this is de facto dozens and dozens of entries which are managed automatically for you in the background. This is all entry families which we're using here. Okay. Does that make some sense? Maybe a bit heavy to read that fast, but the point is that you get the general idea just behind that one, and I think you get the general idea how to handle something like that. Cool. So, handling requests by parameters, or why not? Can I do something like that? I have an entry allocate, an entry free, and I only want to accept the allocate calls if I actually have enough resources to serve it. So depending how much memory this allocate call is requesting, I will block it or not. Sounds sane, right? You only accept this call if the number of bytes requested here is smaller than the bytes which I have. Cool, huh? No, it's not cool. What would that mean?
Just first accept all of them and we'll then check if we don't have enough resources, just requeue it to the block.
What would you expect from the runtime environment if that would actually compile, which it doesn't? So either compiler tells you, bugger off, that doesn't compile. But if your system would accept that, what would your runtime system need to do to implement that?
We have to, because you're reading the parameter, which means you have to get that task to send a message, which means the task is already being sent.
Yeah, that's one aspect of it. Also, how do you select which task will come next? So assume it's not about message passing, assume it's a synchronization point in memory. How do you select the task which comes next?
So what I do, another kind of interesting way to do that is first just accept all of them, say yes to all of the requests, and when they really need to write to the memory, I'll check. And if I don't have that.
Sure. We'll solve that. We just try to find out why it doesn't work by itself.
So, because normally it happens in order.
Priorities, for example. Yeah.
Priority or best in class.
Yeah.
But there might be tasks with lower in the queue that can be accepted.
Yeah.
And so you have to check all of the tasks.
Yeah. And you have to recheck them. You have to reorder all of your tasks every time that comes in. And here it's a linear criterion, which is simple. But this could be as complicated as you want. And this could change depending on your server state. That means not only you need to reorder that when the tasks are coming in, you may actually need to reorder it with every time you actually accepted another task in there. And that blows in your face with respect to any kind of performance. Because then that means you have a longer queue and your performance goes completely out the window. You have to reevaluate everything all the time, reevaluate everything all the time. So this is not practically feasible. There's one theoretical language called SR, which I found, which actually does that, but nobody else on the plant has implemented something like that. And now comes something similar to what you suggested. What you do in practice here, you do it multi-staged. You accept a call in first. And here I'm masking the double interaction. I have to the outside something which is allocate, looking like allocate and free. But to the inside of these, I have a call which indicates what are the sizes so that I can now implement an internal management system which reorders them in the order I want there, and then I can call the action allocate call later, which in this case is an entry family again for efficiency. Double interaction is hidden. Is that good? Why wouldn't you ask the tasks to just do this manually? You don't call this allocate thing, you call the task explicitly, call sign in, and then call allocate. All is good. Sure. First of all, somebody may not be playing by the rule. Second, my server now can no longer rely on the fact that anybody who calls sign in will also call eventually allocate. So the double interaction is in the control of the client, which the client may enjoy because the client has the possibility to withdraw and do something else if he lost interest in this whole operation. But the server may be needing to be much more complicated now because the server has to cater for possibilities that clients are using these interfaces in any kind of order.
So also does that separately, wouldn't it have to sign in and then join the queue again for an allocation? So like you could have a bunch of people waiting to sign in and you could be waiting to get the allocation.
Yeah, that's another problem. And here the server has a little bit more control over that, but the client can no longer get out of it. The client is bound to commit to go through with this. Okay. Double interactions. How does it work with relation to atomicity? So what you usually want to avoid is double interactions which are actually visible from the outside. Anybody who has worked with databases will be shivering by the thought of having these kind of double interactions, that you have to do multiple operations, or two in this case, in a specific sequence so that the integrity stays okay of your system, usually bundling them hard into a single transaction and make the client commit to actually go through with this whole transaction rather than allowing it to split things up. Okay. So requests are no longer atomic. You easily can deadlock the server. You can also easily deadlock the client in the process. How do we solve that? Make it part of an atomic action. Cool. Some would assume that all the clients are nice and none of the clients are dying. Because even if they're nicely programmed, what do you do with the client which just died in the process? That's pretty dodgy. And usually you just eliminate it completely by replacing it with a single request. As here, for example, all kind of requests are going through a central call, the only call which is visible to the outside. And this call to the outside will, behind the scenes, be implemented with an entry guard of true. This is simply by default always open, and you accept anything which comes in and then reorganize your tasks on the inside. Client may or may not have lost all control over that, because what you still have available is, of course, that you can still do a requeue with the board internally to the server. So the server has it under control whether this transaction is still interruptible or not. Sometimes it can be okay that you accept it in, but if the client goes away after that, fine. You haven't changed your internal server state yet. Once you start changing your internal server state, you say that there is no requeue with the board anymore. There is only normal requeue, which kills the abort possibilities for the client side. You remember this from the requeue operations? Not really. Look at your face. Okay, every time you do a requeue, which means you take a task for later processing into another queue, which can be on the same protected object or can be a different task or a different protected object. Every time you do that, your client has not any awareness of that. So your client is just, well, the call went through. It's a bit slow, but doesn't know that he's actually internally blocked. And if the client is in, for example, a select and abort in a timeout statement, where the client wants to get out of that one, the client usually can get out of this if the client is in the outside queue of a protected object. Then you can always get out of this. Nothing happened yet. The protected object didn't actually process you in any way, or the task didn't process you yet. It's in the outside queue. Fine. But what happens if you accept it in and you're re-queued to an internal entry? And the client says, abort, timeout, I want to get out of here. Now, if you have done this with a standard re-queue statement, the client is buggered. Too bad. From the perspective of the client, it looks like it's processing, it's running, even though it's blocked at the moment. But if you say re-queue with the board, you explicitly re-enable the option for the client. Yes, I have done some processing in my server, but I still say requeue with the board so that the client can withdraw that call at a later point in time. You can make all of these decisions here as well. At what point do you remove the possibility from the client to abort this call? Okay, next slide actually does exactly that. So you have your standard requeue and the requeue with abort statements, which is exactly what we just said. Cool. So from the perspective of real-time systems, we would love to have timing constraints as a part of this. Unfortunately and frustratingly, very few real-time systems can express this explicitly, so that your compiler analysis or your runtime system has an actual understanding what's going on there. Nobody stops you from doing this on a parametric level, but that your compiler understands it would be much nicer. Resource requests should be ordered in a way that deadlock analysis is not being violated, so don't try to have multiple or double interactions in the process, which will make your deadlock analysis usually hell. And task failures is always problematic. In your deadlock analysis, in your resource control, you always assume, this is something that most people forget, a standard assumption. In any of your deadlock analysis, you assume that any task which claims a resource will actually release it. You will always only spend a finite amount of time inside your critical regions, which you can verify that this is the case, unless your task just died. So you need to have a way to either automatically do that or some other method to recover from that, which is almost always ugly. Or you guarantee that it cannot die, or if it dies, everything dies. Which is a common practice for real-time systems, that if something actually falls over inside a specific computing node, you just kill this whole computing node and don't even try to recover it. Okay. So, and then the promised section of resource reclaiming, starting from worst case analysis, which may not be so bad at runtime, and reoperating, reclaiming those resources at runtime. We'll now move back into scheduling systems. How do you embed this kind of reclaiming scheme into your actual scheduling? We'll also move to multi-CPU scheduling now. So far, the scheduling which we have seen was all traditional single CPU scheduling. We will now do resource reclaiming in a much more realistic set with schedulers which are actually scheduling over multiple CPUs, which actually makes it quite complicated and quite interesting how to handle these kind of additional resources which may be coming your way. All right, this is as far as I want to drive it today. Next week we do the resource reclaiming and we slowly start discussing larger systems for fault-tolerant operations. I want to run through, before we end the course, I want to run you through a number of practical cases where you can see how people solved high levels of fault tolerance. What can you do to make systems more or less error prone, even if the unforeseeable happens? Most of these error prone countermeasures are dealing with the unforeseeable, which is actually, it sounds funny. You say, well, I'm preparing for the unforeseeable. But it's a quite technical term. You have taken care of all the foreseeable faults in your system, which by definition means beyond that point, you're handling the unforeseen faults in your system. Cool. Enjoy your sunny weekend.